Okay, I think we're ready for action. Welcome, everyone. Whatever that previous talk was must have been a real doozy. Hopefully this one will be boring and short. Okay, so this talk, against my better judgment, is called the Great Sidecar Debate. Now, I didn't want to name it that. So the real name of this talk, which would not have been accepted, is why KubeCon attendees need to take the time to understand a bunch of complicated engineering trade-offs instead of blindly jumping onto the new thing. So that's really what I'm going to talk about. And hopefully, we can lock the doors and you're going to be forced to sit through this with me. So I'm William Morgan. I'm the CEO of a company called Buoyant. We make a service mesh called Linkerd. Hopefully you're familiar with it by now. It's a graduated project, been graduated for years. One of the earliest projects ever, part of to join the CNCF, I think maybe fourth or fifth project. Linkerd's been around for almost 10 years at this point. And I have opinions, which I'm going to share with you. So yeah, get ready. So what's this talk about? This is going to be a talk about sidecars, and I'm going to provide some kind of like non-service mesh, sidecar content, so we're all on the same page. It's also going to be a talk about engineering trade-offs and like how to think through some of the stuff. It's not really going to be a talk about right or wrong, old or new, or good or evil, because I think in some cases the answer is clear, in some cases the answer is not, and the reality is in the vast majority of kind of engineering decisions, the answer is not really that clear. The answer is like, here are the trade-offs, and you have to decide which one makes the most sense for you. So I'll try and present some data, some observations. I'm going to present my opinions and my conclusions, but I'll try and present it in a way where you can draw your own. That sound good? All right. So we're going to talk about sidecars. I'm going to tell you what a sidecar is, which is, the answer is it's just a pattern. And if you go back to like ancient blog posts from 2015, we've been talking about sidecars like even in the Kubernetes docs for 10 years. But we never really had like an object in the API or in the Kubernetes spec, that kind of formally was about sidecars, or formally captured the idea of a sidecar until 2023. So I said sidecars are a pattern. The idea is that you take a container and you run it next to a main container, right? And that's really what it is. So because they're both in the same pod, they share the same network namespace, they're in the same C groups, they share file system through volume mounts. Otherwise, the two containers are isolated, right? Because they're containers, that's the whole point. And they run basically as long as your application runs, your application being the main container. And when your app terminates, so does your sidecar. I put an asterisk there because there have been advances in sidecars over the past couple of years. So in the case of something like Linkerd, we have this thing called the Linkerd proxy, which is this little Rust application, and we stick it right in there. And your application is in there, and we have this init container called Linkerd init. I'm not going to go into like too many of the gory details of how this works. I've given probably 1,000 extremely boring talks about how service meshes work at this point. But so there's many other examples. So here's an example. I think I stole this from some Kubernetes doc somewhere. We got the streaming container is like another sidecar. That takes your logs and sends your logs to like a logging backend. There's a couple other examples. Vault there's a sidecar, open telemetry, and of course service meshes. Here's like, I don't know, at the time of this screen cap, this was like the set of service meshes in the CNCF landscape picture. And so like that's the idea, right? It's a pattern. Okay, and why? Like, why do we care about this? Well, it's a really convenient way to add functionality without having to change the application, right? As opposed to a library or something where you have to, at a minimum, recompile the application. So it can be language and framework independent. It can be owned by the platform team instead of by the developer team. That's a good one for us as operators. And then the other really nice aspects, and I'm going to talk more about this kind of in the second part of the talk, is they have a really clear operational model, right? Every sidecar container belongs to the pod, so you treat it just the same way that you treat any other pod. If that thing dies, it gets restarted, just like any other container. If the pod dies, you can restart the pod. It's got a really clear security model, right? In the case of a sidecar, a service mesh sidecar, where the sidecar handles all traffic coming to and from the application, it's kind of like the little firewall for that pod, right? So the security model is pretty clear. And it makes use of all this massive technology investment that we've done for isolation, right? So the whole point of containers is isolation, right? It's making sense so far? All right. I guess I gave away the punchline to this, right? Like, here's how this works for service meshes. The sidecar, proxy sits in there and it handles all traffic to and from the application container, right? We don't have to delve into that. Linkerd has this particular implementation, but really, it's kind of like independent, right? We have this Rust micro proxy. Lets us do all this fancy stuff. We write it in Rust. We can avoid all the kind of security bugs that are kind of a fact of life with C and C++. But sidecars have downsides as well. I put r/work because some of these I'll talk about in a minute. Some of these have been eased, right? So what are the downsides of sidecars? The first one is that, like, if a sidecar is really big, then it sucks, right? And this, for those of you who are old enough to remember Linkerd 1.x, which was written on the JVM, the smallest we could squeeze that thing down was like 150 megs. And so if you have a 50 meg like Go microservice, and then we're asking you to put 150 meg proxy next to it, well, you're like, it's not really the like lightweight thing you would expect, right? Side truck is what I call it. The other downside is that pods are immutable. So if you ever need to change the sidecar, that means you have to restart the pod and you have to restart all the containers in there. If your application is not built for that, well, that's a big problem, right? Now you have to tie the sidecar or the service mesh or whatever, kind of technology the sidecar is implementing. You have to tie that lifecycle to the application lifecycle. Now, hopefully we're all much better at writing applications these days, and we're used to building things for Kubernetes, and we realize that Kubernetes can restart our pods at any point for any reason. There's no guarantees, and it's not that big of a deal. But if you've got legacy applications, it could be a big deal. Another downside of sidecars historically has been job termination. So if you're running a job instead of a kind of continuously running service, then you have to synchronize the termination between these two containers. Init container race conditions, regular container startup ordering race conditions, it's a bunch of other things here that are kind of range from like severe to warts. This is like pneumonia to warts, I would say. I think the other problem with sidecars, which is not really recognized, and this is more of a psychological one, is that you see the sidecars. Right? So for service mesh, if you think of the service mesh as a networking model, then it's weird to see this component kind of like alongside your application component. We're used to the network being independent or invisible, and like the network engineers handle that, and we as beautiful pure ops people don't have to handle that. But now you're seeing it, so it's weird. And you get to see the usage too, right? If this was like a fat client library, right? If this was like a really rich gRPC library and it was doing all this stuff, the resource usage of that gRPC library would be kind of built into the resource usage of the application as a whole. You wouldn't see it pulled out, but now we see it pulled out, and so now we have this obvious thing that maybe we didn't want to be obvious, and we can see just how much resources it consumes. I'll skip this I'll skip this tweet which I since deleted. I had a funny in quotes eBPF joke. So yeah, sidecars, historically have had these rough edges, and I'm going to run through this kind of on the fast side this next bit, where I'm going to talk about the evolution of the sidecar, like KEP and how it eventually got integrated into Kubernetes. It's kind of interesting from like historical perspective, but modern Kubernetes versions have native sidecar containers, all graduated to GA, and like everyone should have access to the stuff now. So some of these problems have been eased. So in Kubernetes, as you might know, we basically have two kinds of containers. There's init containers and there's regular containers. They just call them containers, right? And init containers kind of get executed in sequence, and they have to run to completion before you get to the next one. And then the containers themselves start in parallel, at least ostensibly, and they just keep running. So if you're, if it's circa 2020 and you're deciding where to put your sidecar, can you put it in an init container? Well, not really, because only one init container can run at a time, right? And like it waits until that's done until the next one starts. So you have to put it as a regular container. But what if your application starts, right? The regular containers all start at the same time. What if your application starts before the sidecar? Well, then things get tricky, right? Especially if you have an init container that has done like some network magic in the beginning that said all communication to and from this pod has to go through the sidecar container. The application container starts up, it wants to talk through the network. It's being routed because that init container has been routed through the sidecar, but the sidecar hasn't started. Well, what happens is things don't work. Okay, you can, there's some hacks. These are like years of pain and effort that I'm just glossing over in these slides. Okay, so there's some hacks you can do. Ostensibly containers all start at the same time, but unofficially the container only starts after the previous container's post-start hook is finished. So, if you put your sidecar container first, then you're okay. We've got a similar challenge around pod termination. If anyone has been running a service mesh prior to 2022 or something with jobs, you'll definitely know this one. If you have a job, it terminates. Your main container is done, like it exits. That's the point of a job, but Kubernetes didn't have a way. I say doesn't, but this is past tense. Didn't have a way to know that the sidecar container had to exit. So, you had to like tell it this via outside tooling. Okay, and there's like some more annoying stuff. Don't worry about this. It sucked. And so, these ideas, like the notion of a sidecar has been with us since 2015, and the realization that there were all these warts has been around since 2019. Right, with this KEP first proposed, and the basic idea was, well, part of the reason why we have these issues with sidecars is because we're not treating them specially, and they kind of have this. We're treating them as regular containers, but they have this kind of this special behavior. And so this KEP has this long, sordid history, all these concerns, and people worked really hard, and then it became a meme on r/Kubernetes because it never got merged because it's a tough challenge. Finally, at the end of 2022, we kind of have this the story taking shape. And I'm rushing through this because like I said, it's stuff that happened in the past. It's ancient history. We don't have to know about it anymore. And so, but the solution here, and for those of you who have ever heard the term native sidecars, the solution here is that we actually are going to add, or we did add some functionality, the Kubernetes community, to init containers. And we added this thing called a restart policy. And we gave it the ability for us to say always. Okay, a bunch of other stuff hasn't been done yet. But with this idea, init containers with the restart policy always flag will no longer block starting of other containers, even other init containers. So they kind of start, with a ampersand after them. And if they ever die, they just get restarted automatically, right? That's why we call it restart policy always. Okay, and we get some new shutdown behavior. So if you marked your container as restart policy always, now you have this new behavior where when the application container stops, you get this kind of reverse automatic termination of all these init containers. Okay, so if you were following along and like adding all those changes up in your head, basically at the end of this KEP, which finally got merged in 2022 or whatever, we've actually solved a bunch of problems, a lot of the warts with sidecars, right? We can guarantee the sidecars initialize before the application container. We can guarantee the sidecars terminate after the application container terminates, and that termination is now predictable. And so, back in 2024, I guess it really only got merged in 2023. So back in 2024, Linkerd and a bunch of other service meshes kind of all took advantage of this, right? Now we have native sidecar support. So if you remember that long list I had ranked from like pneumonia to warts, we solved the warts. The pneumonia still kind of remains. All right, so far so good. You can like erase all that from your brain because now we fixed all those problems. All right, so sidecars versus alternatives. Here's where we get the debate portion. If you look at the set of service meshes today, there's kind of three basic approaches. There's sidecars, of course, which I've talked ad nauseum about. There's what I would call node proxies, where we're going to put Envoy, or in the case of Linkerd 1.x, we're going to put the Linkerd 1.x JVM thing on a per node basis, or there's ambient. The thing to realize is that, for the heavy lifting of service mesh features, for anything that involves understanding HTTP requests or HTTP2 or gRPC, they all use L7 proxies. There's no getting around that. Even if you have eBPF in there, you still have to fall back to an L7 proxy for those service mesh features. So the only question is, where do you put the proxy? And that's where things get interesting. Right, so sidecars, hopefully you know this by now. You put them in each pod, right? Istio has a sidecar mode, Kuma, Linkerd 2.0 and beyond. You get one proxy per pod. Node proxies, as you might expect, you deploy a proxy per node. And so you have every application on that pod share the proxy in that node. That makes sense? Ambient is where things get tricky, and I just borrowed the diagram from the ambient docs, so I didn't want to try and recreate it. So here we actually split it into two kind of parts. We have the L4 part, and we have the L7 part. And L4, I think in this context, basically means MTLS, and kind of like TCP connection handling. And then L7 is what they call the waypoint proxies. So that's Envoy, and those go somewhere else. So the in this mode, L4 is deployed per node, and L7 is put somewhere in kind of a tunable level. And this is what I think makes this model kind of interesting. I wouldn't call myself an ambient expert. I'm like a ambient student from outside. But this is what makes this model interesting, because you get a kind of a knob that you get to turn and where you place those waypoint proxies. And that knob can be anywhere from I'm going to do a lot of sharing to like I'm going to do no sharing. And we'll see why that becomes interesting later. In this example, so ztunnel is the L4 proxy here, the two green boxes on the left and right. And then the waypoint proxy is L7 and proxy in the middle. In this example, it's deployed, I think, on a separate node, but really that waypoint proxy could be deployed in a variety of ways. Okay, so you'll notice that the fundamental difference here between sidecars and non-sidecar approaches is the use of shared proxies. So in sidecars, by definition, you don't share the proxy between pods. For node proxies, every pod in the same node shares that same proxy. And then for ambient, every pod on the same node shares the L4 proxy. And then the L7 proxy gets shared by like whatever you've configured. And you can configure that to be like everything in a namespace shares that same pod. You can configure it to be everything with the same service account shares it. You can configure it, I think you can configure it to be no sharing mode. It's tunable. But sharing means multi-tenancy, and this is where things go wrong. And the reason why I know this so well is because of our days with Linkerd 1.0, before we moved to the sidecar model. This was the early days of deploying Linkerd in production with a lot of our adopters, and this is where we learned some of the pain, and it's part of the reason why we ended up adopting the sidecar approach. So multi-tenancy, of course, means like different tenants, different applications or customers, or however you want to say it, different applications in our context, sharing something. That's a huge challenge for any system. In fact, this is contended multi-tenancy, which is like the applications that are running on your Kubernetes cluster aren't cooperating with each other by design, right? They're kind of like independent, and you rely on the system to provide fairness. And there's lots of examples of this. This is like an example. This is like a historical challenge for any kind of computing, right? Different users running programs on the same computer, VMs sharing the same physical host, containers, applications sharing the same proxy. These are all examples of independent components, trying to all access the same shared resource. And I think what's really the part that's important to understand is that there's different types of, there's like a qualitative difference between L4 traffic and L7 traffic. L4 traffic, if you look at if you look at the Linux kernel and the way that it enforces sharing. So operating systems are kind of like the canonical example of how do we enforce fairness in these contended multi-tenancy situations. If you look at what they do for L4 traffic, you've got a set of tools like queuing disciplines and rate limiting and so on. You can kind of treat these as event level decisions, right? But when you go to, and that's how the Linux kernel ensures that no one application can starve the others of access to the network resource. When you go to like CPU and memory, and like how do we make sure that one application cannot stop another application from running, can't steal all the resources from another application, it gets much harder. Applications are kind of unbounded in a way that L4 that L4 networking is not. So the sharing there, the fairness there is enforced through things like timer interrupts and preemption. This is like preemptive multitasking. Task scheduling, memory management units, that kind of stuff. And L7 request processing is much more similar in profile to applications. When your task is parse an HTTP request and do something with it, it's kind of like an unbounded amount of work that you have, ahead of you to do that. And modern network proxies, even the Linkerd proxy is not really designed to enforce fairness between clients. So that's the situation that we're in that we've tried to avoid in Linkerd is having to share kind of contended application usage through the same proxy. It's something, one could design a proxy to do this. None of them have been designed. Right, so what are the actual problems concretely, right? And I'm gonna pick on ambient a little bit because that's the popular kid, so you gotta pick on the popular kid. Noisy neighbor issues, right? That's a big one. You can overload a proxy with one application and then the other, other applications that rely on the same proxy are unable to use it. Okay, you can do this in Istio, in ambient, by setting limits on the waypoint or on the Z-tunnel, increasing traffic on one application, and you'll see another application bogged down. Okay, great. That's what we would expect, right? Single points of failure, obviously, the blast radius gets higher. All pods shared by this proxy. If a proxy goes down, then all the pods shared by the proxy go down. And that, all pods, that's the blast radius. That could be one pod. It could be arbitrary pods from arbitrary applications, or it could be all pods from the same application, or all pods in a namespace. And then, the third one is kind of appropriate sizing of resource limits and requests. If, like me, you have struggled with setting resource limits in Kubernetes and navigating that in practice, you can imagine, how hard that is for one application. Well, how do you do it for a proxy that has to handle arbitrary applications? None of those issues are deal breakers, right? Those are all trade-offs that you're making, right? And I think what's interesting about ambient is that it gives you kind of a knob to turn, which is, where do you provision the waypoints? You can, like I said in the beginning, you can kind of move anywhere from very shared to not shared at all. But, you pay a cost for doing this, right? You've got extra hops, you've got extra complexity, you've got extra tuning that you have to do. Okay, am I coming up on time? Is there a timer in the back? I want to make sure I'm not going over. All right, in our benchmarks, so the question is, are the trade-offs worth it, right? And this is a question for us as Linkerd maintainers. That's a perspective that I want to bring to you, because I don't think ambient is bad, right? But the question for us is is this a trade-off that's worth it for Linkerd? I like the architecture, in fact, in many ways. In our benchmarks, and benchmarking is an art as much as it is a science, but this is our best effort to do kind of apples to apples comparison. Linkerd still seems to be smaller and lighter in terms of data plane, memory, and CPU than ambient. And it still seems to be faster, sometimes significantly faster than Istio ambient. So, benchmarking, like I said, it's dependent on the application. It's dependent on very specific things. I'm sure you could find examples in the other direction. But when we've evaluated this is what we found. So I guess if I were to summarize this, kind of the goal here was to expose to you some of the trade-offs that happen and the things that we try and think through on behalf of Linkerd users. We do periodically kind of review these other approaches to Linkerd. I think the analysis that we keep landing on, and maybe this changes in the future, right? But the analysis that we landed on today is that the majority of the problems that ambient seems to solve are not really relevant to Linkerd. The increase in operational complexity doesn't really make sense for us. Not restarting your applications for our users doesn't seem to be a huge win, although I think if you were a cloud provider and maybe you didn't want to put, kind of platform components in the application pods, maybe that would be a big win. So sidecars continue to make the most sense for us, but we do continue to we do reevaluate this decision periodically. Okay, so that's kind of the end here. I've got an ad. You can, if you want to learn about service meshes, we've got a thing here. I've done my best to kind of be, fair and open-minded about this, but I'm definitely happy to answer questions to the extent that we have time for that. So, thank you very much for sitting through that.